1939, North Sea, winter gales. A British tribal-class destroyer pushes through heavy seas at over 30 knots, hunting a German surface raider. 60 miles south, a German Type 1934A destroyer loses her port engine. Again. Her Wagner high-pressure boilers, running at over 1,000 pounds per square inch, have failed for the third time in 2 months. Her crew scrambles to isolate the fault while the ship wallows on her remaining plant. The British destroyer carries Admiralty 3-drum boilers, running at just 300 pounds per square inch, less than a third of the German pressure. Naval engineers in Berlin called the British approach primitive, outdated, unambitious. Both navies designed their destroyers for 36 knots. On trials, the German ships sometimes exceeded 38. But trial speed is not combat speed. In the freezing North Atlantic, with fouled hulls, fatigued crews, and machinery running month after month without a dockyard, the gap between what a ship could do and what it actually did was the difference between fighting and drifting. The engine the Germans dismissed as conservative kept British destroyers at or near their designed speed when German machinery routinely failed to deliver, not because British boilers were more powerful, because they actually worked. The problem facing every destroyer navy in the 1930s was the same. How do you generate enough power to push a 1,500-ton warship to 36 knots while leaving room for guns, torpedoes, depth charges, and fuel? Steam pressure was the obvious lever. Higher pressure meant more energy per pound of steam, smaller boilers, lighter machinery, and more displacement freed for weapons. Germany pushed this logic to its extreme. The Kriegsmarine adopted the Wagner high-pressure boiler system, operating at 70 atmospheres, over 1,000 pounds per square inch, at temperatures exceeding 840 degrees Fahrenheit. A subset of their destroyers, Z9 through Z16, used Benson-forced circulation boilers at an astonishing 110 atmospheres, over 1,600 pounds per square inch. 6 of these boilers per ship fed turbines rated at 70,000 metric horsepower, nearly double the output of a contemporary British destroyer. On paper, German destroyers were engineering masterpieces. In practice, the machinery created problems that plagued the Kriegsmarine throughout the war. The issues were systemic. Superheater tubes cracked and corroded from carbon dioxide and oxygen in the feed water. Superheated steam at those pressures is invisible, so leaks destroyed wiring and cables before crews could even find them. Saltwater ingress could shut down an entire boiler group without warning. The automatic control systems for air, water, and fuel regulation were too complex for human operators to manage under combat stress. Boiler rooms housing approximately 20,000 horsepower each were so cramped that individual valves were physically inaccessible. Engineers could not see the burner fires from the central control position. Spare parts were rarely available at forward bases, and systematic preventive maintenance was difficult to sustain until procedures were overhauled after 1942. Z10, Hans Lodi experienced a 100% turnover of engine room officers, 42% turnover of warrant officers, and 62% turnover of ratings in just 13 months of war. Training time for German engine room crews had been cut from 54 months to 31 months. The machinery demanded experienced specialists. The Kriegsmarine could not retain or produce enough of them. The Admiralty chose a different path entirely. The Admiralty 3-drum boiler emerged from the fuel experimental station at Haslar and entered service with the A-class destroyers ordered under the 1926 program. Its design was deliberately conservative. 1 steam drum at the top, 2 cylindrical water drums below, roughly 400 crank tubes per water drum, each about 1.5 inches in diameter. Operating pressure 300 pounds per square inch at 600 degrees Fahrenheit. The superheater sat inside a gap between tube groups, with steam flowing at 150 feet per second to prevent tube distortion. Specific fuel consumption ran about 0.8 pounds per shaft horsepower per hour. Not spectacular, but utterly reliable. The Admiralty had tested higher pressure alternatives. HMS Acheron carried experimental Thornycroft boilers at 500 pounds per square inch and 750 degrees Fahrenheit, achieving 25% better fuel economy. The Admiralty examined those results and concluded the savings did not justify the added complexity and risk for wartime operations. They chose the 300-pound system and standardized it across the fleet. Several design features made this boiler ideal for sustained naval operations. The tubes entered cylindrical drums perpendicularly, allowing reliable thermal expansion without the stress failures that plagued angled entry designs. The cylindrical water drums eliminated grooving, a fatigue failure that cracked non-circular drums. Natural water circulation worked without external downcomers, and critically, the moderate operating pressure tolerated imperfect feed water quality, crew mistakes, and battle damage. A hastily trained wartime stoker could operate these boilers safely. In a global war fought increasingly by reservists and conscripts that mattered more than any efficiency figure. The turbines paired with these boilers traced their lineage to one of the most dramatic demonstrations in naval history. In 1897, Sir Charles Parsons raced his experimental vessel, Turbinia, through Queen Victoria's Diamond Jubilee Fleet Review at Spithead. 100 feet long, 44.5 tons, 9 propellers on 3 shafts, powered by his compound steam turbines. She made 34 knots. No Royal Navy vessel could catch her. The fastest destroyers of the day managed 27. By 1906, Parsons' turbines powered HMS Dreadnought, the battleship that made every other capital ship obsolete. But direct drive turbines had a fundamental problem. Steam turbines run most efficiently at thousands of revolutions per minute. Ship propellers work best at 200 to 350. Parsons solved this with reduction gearing, using double helical gears to step down turbine speed to propeller speed at 98.5% efficiency. The first geared destroyers entered Royal Navy service in 1913. From 1915 onward, every new British destroyer used fully geared turbines. By World War II, the standard configuration was 2 Parsons-geared steam turbine sets on 2 shafts, each with high-pressure and low-pressure turbines driving 3-bladed propellers through single reduction gearing. Simple, proven, maintainable. If you are finding this deep dive into Royal Navy engineering interesting, subscribing takes a second and helps the channel produce more content like this. The specifications tell the story clearly. A British Tribal-class destroyer displaced 1,854 tons standard, carried 3 Admiralty 3-drum boilers, producing 44,000 shaft horsepower, and made 36 knots at designed load. HMS Cossack achieved 36.2 knots on trials. Range was 5,700 nautical miles at 15 knots. The later JK and N classes pioneered a critical innovation, reducing from 3 boilers to 2 while maintaining 40,000 shaft horsepower and 36 knots. The Battle class, the ultimate expression of the system, achieved 50,000 shaft horsepower from just 2 boilers, the most powerful British destroyer plant of the war. Germany's Type 1934. A destroyers also designed for 36 knots, and on trials some exceeded 38. But designed speed assumed all 6 Wagner boilers functioning correctly, which rarely happened for sustained periods in service. German destroyers suffered an additional design flaw that compounded the propulsion problem. Top heaviness required 30% of fuel to be retained as ballast, reducing effective range from the designed 4,400 nautical miles at 19 knots to roughly 1,800 to 2,000. British tribals carried 5,700 nautical miles of range. In practice, German destroyers operated with roughly a third of that figure. The battles of Narvik demonstrated what happened when these design philosophies met combat. April 10, 1940. 5 British H-class destroyers attacked 10 German destroyers in Ofotfjord at dawn. Multiple factors converged against the Germans. Their ships were critically low on fuel because their high-pressure machinery consumed it rapidly, and only 3 had completed refueling. The British achieved tactical surprise. They torpedoed and sank Wilhelm Heidkamp, killing Commodore Bonte, and destroyed Anton Schmidt. German destroyers in outlying fjords needed time to raise steam in their complex boiler systems before they could respond. 3 days later, HMS Warspite and 9 destroyers, including tribals Bedouin, Cossack, Eskimo, and Punjabi, destroyed all 8 surviving German vessels. Dieter von Roeder and Erich Gieser, both suffering engine difficulties, fought while docked, unable to maneuver effectively. Geography, surprise, ammunition exhaustion, and the absence of resupply all played decisive roles. But German machinery limitations, excessive fuel consumption, and inadequate effective range compounded every other disadvantage. 10 German destroyers lost. Half the Kriegsmarine's destroyer strength gone in 2 engagements. The pattern repeated across different theatres. Bay of Biscay, December 28, 1943. 2 British light cruisers engaged 5 German Type 1936A destroyers and 6 torpedo boats. In rough seas, German destroyers proved poor sea boats with waves breaking over their bows. The Germans fired 34 torpedoes in 8 attacks. Every single one missed. The British sank 3 German vessels while sustaining minimal damage. At the Battle of the Barents Sea, December 31, 1942, British destroyers aggressively engaged the heavy cruiser Admiral Hipper and pocket battleship Lutzow to defend convoy JW51B. The British screening force, though massively outgunned, maintained sustained high-speed maneuvering under fire for hours, a tactic that demanded consistent machinery performance under extreme stress. This engagement so embarrassed the Kriegsmarine that Hitler threatened to scrap the entire surface fleet. The comparative picture extends beyond Germany. The United States Navy struck a pragmatic middle ground with Babcock and Wilcox boilers at 600 pounds per square inch, exactly double British pressure but about 40% of the German figure. American Fletcher-class destroyers achieved 60,000 shaft horsepower with good reliability. The French Le Fantasque class held the world destroyer speed record at 45 knots. But a French liaison officer with the United States Pacific Fleet delivered a telling post-war verdict. High-powered machinery was too delicate, consumed too much space, and required too much fuel. Tactically, it bought nothing. France abandoned high-speed pursuit in its post-war destroyer designs. No major navy adopted the German high-pressure approach after the war. Over 200 British destroyers used the Admiralty 3-drum boiler and Parsons geared turbine combination between 1929 and 1947. The War Emergency Program alone produced approximately 112 ships with this standardized plant. A stoker trained on HMS Cossacks boilers in 1940 could step aboard a new destroyer in 1943 and find essentially the same equipment. Spare parts were interchangeable across the fleet. Dockyard procedures were universal. This logistical advantage, invisible in any specifications table, proved as valuable as any technical parameter in a 6-year global war. The Admiralty 3-drum boiler and Parsons geared turbine did not win any specifications competition. 300 pounds per square inch was modest by contemporary standards. 0.8 pounds per shaft horsepower per hour was unremarkable. 36 knots was matched on paper by every major navy, but paper specifications do not sustain campaigns. The real measure of a propulsion system is not what it achieves on trials in calm water with a fresh crew. It is what it delivers after 6 months in the North Atlantic, operated by men with 4 months of training, 1,000 miles from the nearest dockyard. Germany designed for peak performance under ideal conditions. Britain designed for sustained performance under the worst conditions imaginable. The wreckage at Narvik, the failed torpedo attacks in the Bay of Biscay, and the chronic machinery breakdowns that limited Kriegsmarine operations throughout the war all point to the same conclusion. In sustained conflict, the system that works reliably in average hands will outlast the system that performs brilliantly in ideal conditions, but degrades under stress. The Admiralty understood this. They chose the engine that would work on the 1,000th start, not just the first. And across 2 decades and over 200 ships, that choice was vindicated by every campaign the Royal Navy fought.